have a lot of time. And this is going to be a lot slower on the video that you're going to be watching this weekend. Sometimes I think it's a little bit better to be face-to-face rather than trying to see what I have on the board and then me acting things out. It's going to be fast and furious. There's going to be some terminology. And then next week, if you have more questions after you've watched the videos, you should come to me. Make some time during office hours. Maybe even come tomorrow if you watch the video tonight. Make good use of your time. Every single cell in your body, every single one, is set up like a battery. Do you know what a battery looks like? Mm-hmm. What do you notice about it?
There's like two different ends.
Positive and negative. Exactly. So the word for that means it's polarized. Separation of charge. That's what that means. In our body, our cell membranes not only separate chemicals, separates charges. We've learned about chemical gradients. We know across the cell membrane, potassium's higher outside the cell than inside. That's a chemical gradient. There are also electrical gradients. We have separation of charge. The inside of the cell is more negative than the outside. So I want you to draw negative charges inside the cell. And to help you remember that the inside is more negative than the outside, then that means the outside is positive compared to the inside. Okay? Scientists have measured the actual values that goes with this separation of charge, just like a 9-volt battery. It tells you how much stored energy is in there. Okay, so scientists have put in electrodes and they can measure how negative the inside is. The students say, why not measure the outside? Because the outside can change. Our outside of our cells, those are called extracellular, outside body fluid compartments, and those change. Take a drink. Take a drink. You're changing your extracellular body fluid compartment right now. Those change. The inside should not. So that's our reference point. The inside of the cell is about minus 70 millivolts. Minus 70, okay? It's minus 70. Now, up at the top of this, yeah, they can see. And this is what you can't see in my video because I acted it out. So now I'm drawing it and I'm recording this, okay? Pretend this line up here is a number line, just like what you saw when you were in grade school. The middle of it is 0, correct? What sign did the digits have to the left?
Negative.
Negative. So minus 70, let's put it over here. Good? Okay. And over here, we'll go to we'll say plus 55. So that's our number line. Now, the next thing I want you to know is, why is the inside of the cell negative? That's important. There are 3 big reasons why. 3 big ones. 1, and this is not in order of importance. Inside the cell, we have a lot of proteins. Of course we do. That's where they're made. And because of your body pH, because of the pH you have, those proteins are negatively charged. I won't go into why your pH makes them negatively charged. That's for chemistry. We go over that again in physiology. You are just learning. Right now, please accept it. I know that's blasphemy in a classroom, but we have limited time. If you want me to tell you what, stay, and I will. So we have a lot of negatively charged proteins. I just draw them as squiggles. moving negatively charged proteins. That's one reason. 2, on the cell membrane, we have a pump, and that pump is moving 3 sodium out for every 2 potassium it brings in. Remember, that's the sodium-potassium ATPase, primary active transport. Sodium has a plus charge, so we have 3 plus charges leaving. Potassium has a plus charge as well. Is this equal swapping of chemicals? No, it's 3 to 2. Is it equal swapping of charges? Still 3 to 2, isn't it? We are losing more positive than what we're gaining, aren't we? And if you lose your positivity in life, what do you become, Jason?
Negative.
Negative. You become negative. Same thing with the cell. If it's losing more positivity, then the inside becomes more negative. Does that make sense? Here's the third reason, and this is the most important reason. And I will not and do not prove to you why it's the most important reason, but in physiology, I sure do. So again, I'm going to say, please accept it. The most important reason is because this potassium is in high quantity inside the cell compared to outside, there are also potassium leak channels. And that potassium wants to go right back out, down its chemical gradient. It wants to leave, and it does leave. So the cell is again losing positive charges. Do you agree? And so what stays behind? Well, sodium is still positive, but the remaining, we become more negative. If we lose positive, then the inside gets even more negative. Now, it pretty much holds steady at around -70 because of the sodium-potassium ATPase. I like to think of it as the mom cleaning up house. If these kids made a mess. Potassium, you're supposed to be in here. Sodium, you're supposed to be out there. And so it's constantly trying to clean up the mess, and then potassium's like, yeah, I'm gonna go back out. The more leak channels you have, the more potassium leaks. So this magic number, -70 millivolts in textbooks, is called resting membrane potential, RMP. Do not let those words bully you into submission. Potential means separation of charge. That's it. Stored energy. Your battery. Your battery, when you put it in front of you, think of that, oh, it's that resting membrane potential. The charges are not moving. You don't have it in a device. So you're not engaging the electrodes. Potential. Separation of charge. That's all. Some cells have more potassium leak channels than others. And that means more opportunity for potassium. You're like, oh, I'm out of here. So can you guess what happens to their resting membrane potential? Can you guess? What'd you say, Amber?
It's more negative.
It is more negative. So when you read textbooks about potentials and membrane potentials, they give you these numbers, and students think all cells are like that. That's just an average number. There are some cells that are more negative than others. That is not for us to worry about. But in physiology, we do. It's important. We're just learning. So good, we have -70 as our starting point. Generic, average, let's use it. You now know the big 3 reasons why the inside of a cell is negative, don't you? Negatively charged proteins, the sodium-potassium ATPase. We say it's electrogenic. We lose more positive charges than what we gain, so that means a net loss of positivity. And the most important that you just have to accept are these potassium leak channels. Potassium wants to leak out of the cell, leaving behind more negativity. Are you okay? Okay, new word. New word. Hyperpolarize. Hyperpolarize. Arguably, we could turn this into a poli-science class. We could say our country is definitely polarized right now and seems to be getting hyperpolarized. Hyperpolarized means more negative. So which way would I move? I would go more negative, wouldn't I? It's hyperpolarized. Okay, good. Depolarized means less negative, getting closer to positive. If I move to the right, I'm depolarizing. I can depolarize a lot and turn the inside of the cell positive. What? And in some cells, they can do that. And when we switch from negative inside to positive inside, that's for us, it's a big amount of current for us. That's an electrical current. And when you plug your devices in and you allow electricity to run through them, you can do work with them, can't you? What happens when your cell phone battery goes dead?
You need to charge it.
Right. Can you use it?
No.
Because you don't have any more separation of charge. You've allowed them to go down their chemical and electrical gradient, and they have reached equilibrium. Yeah, done.
Your laptop might fall down because the thing in the back is, there we go.
Thank you.
I have a service too. I'm worried about it.
Thank you. You have excitable cells. They are muscle. That's what you're learning about this weekend. Neurons. All muscle is excitable. These are cells that can go from negative to positive and back to negative again. And that means they are generating electrical current, and you can do work like move, contraction. And that's your focus this weekend, is to learn about skeletal muscle contraction. And it starts here, understanding where the electrical current comes, because electrical events precede mechanical. When you get your phone for the first time, you might need to charge the battery before you can use it. Electrical events must precede mechanical. Okay? So, move me. Hyperpolarize. Which way should I go? And that's what I'm doing when you hear me on the video when I'm saying, move me, and all of a sudden I'm gone. This is our number line, okay? I drew it up here so you can visualize that. Depolarize. Good. Okay. Now, real quickly, I'm going to murder Jason.
Oh dear. Jeez.
Now, I want everyone to know on YouTube that no student was directly harmed in this demonstration. Are you a compliant participant?
Yeah.
Okay, see, I have her permission. So silly. Very bad example for these times, but it works. I'm going to shoot you. And I shouldn't even make this. The person is being sued and going to jail for doing this for the hand.
How
the
old?
hand. It was a few. Anyway, I'll explain after. We are playing, and I do not mean her any threat. I like Jason, so I'll pull the trigger slowly. Why doesn't that make sense, Shelby?
Wouldn't you want to kill her quickly? So it's painless, right? I'm tired.
You have never shot a gun. Okay. Has anyone here pulled a trigger to a gun? That's why everyone's laughing behind you.
I figured
It's
that.
okay. There is this thing called trigger point.
Mhm.
When you pull that trigger, doesn't matter how quickly or slowly you pull the trigger, that bullet fires with the same force. Does not matter if I BAM! Or, I like you. A bullet's going to come out with the same force, regardless of how I pulled the trigger. Okay? Okay. So that's why it's silly, right? Doesn't matter if I... So trigger point. Muscle and neurons, excitable cells, also have a trigger point. But we don't call it that. It's an all or none. It's an all or none event, just like pulling the trigger. You either reach trigger point or you don't. There's not, I killed her a little with the bullet. There's no such thing. It's all or none. You either reach that point or you don't. And in excitable cells, this is called threshold. Okay, threshold. It's all or none. You either reach it or you don't. In order to reach threshold, and I'm almost done, so bear with me, you have to depolarize the cell. So move me. You have to depolarize the cell to reach threshold. I'd be moving this way. Good. Scientists have measured this, and again, threshold is given a number, but it's an average number. It depends on the cell. Just like if you've ever fired more than one kind of gun, you know they all have their own trigger point. Have you ever driven a stick shift car? I was going to say, maybe I can get the analogy there.
No, I understand that.
Okay, they all have their own trigger point. And when I fire different guns for the first time, I don't know what it is. And I'm scared and I'm hesitant. And I'm like, And my head is like, just pull the trigger. I'm worried about the kickback. Once you fire it more and more and more, you anticipate. Mm-hmm. So most textbooks say the magic number for threshold is -55. Please understand, that's just an average number. Not all guns have the same trigger point. That means, on average, we need to depolarize by 15 millivolts. That's what we're talking about. And then something amazing happens, Amber. When we depolarize enough, an all or none event happens, like the firing of the bullet. And the cell allows a great amount of positive charges in, and it gets very positive. But it's very short-lived. And then the positive charges leave, and we go back to negative. And when that happens, that's a lot of current, both ways, and we can do work. So we depolarize, and then we repolarize. Repolarize means to go back toward resting membrane potential. Hyperpolarize me. Good. If I go back to resting, that's also repolarization. I can depolarize, repolarize. I can hyperpolarize, repolarize. Repolarize means to go back toward your starting point, resting membrane potential. I saw a hand.
That was me, and I was going to ask what number you'd be at when you're repolarizing. Would that be the -70?
Yeah, that's where, but see, when the neurons, muscle, when excitable cells do this and then repolarize, they overshoot. they'll actually hyperpolarize for just a little bit. And then they're like, oh, I should have stopped over here. Okay, that's a phenomenon. That does happen. Okay. That is called an action potential. That's your electrical event. From that, you can do work, and you can contract. In the video, you're going to hear me tell you how a neuron innervates skeletal muscle. Skeletal muscle needs a neuron to start an action potential. In the video, you'll hear me describe how the neuron has to have an action potential in order to release neurotransmitter onto the skeletal muscle to get it to depolarize enough to reach threshold and have an action potential so you can have contraction. Your heart does not need a neuron to do that. And we'll address that in another unit. So pay attention to the somatic motor neuron. That name tells you it's the neuron that innervates your skeletal muscle, what we call voluntary effectors. You can voluntarily stand up and leave. The somatic motor neuron has to tell the skeletal muscle, now's the time for you to have your action potential, and for you, as a result, to have a mechanical event. Muscle contracting allows us to move, but you know what? I'll leave you with these thoughts. You also have to have it relax. You can't move if you're in tetany, spastic paralysis. You cannot move. You also cannot move if you're in flaccid paralysis. Our movement, even when we walk, we require with every step contracting one muscle group, relaxing another, and then in the next swinging of our foot, switching them again. Hamstrings, quads, hamstring, quad, hamstring, quad. And there are some people that cannot switch off the muscle groups like that, and they have dyskinesia. What is that? Parkinson's disease. So I'm trying to make the connections here of why you care. In the video, I tell you why it's so important for relaxation, and I say you better know what is required for relaxation. And I tell you some very sad stories of people who were poisoned and they died from asphyxiation because they could not relax their muscle. And sadly, that poisoning is still happening. So, now you want to go watch the video, don't you? Bye. Sorry that I went a little over.